Well, hello, NAR 346, and thank you for sticking with this course up to this point. I hope that you understand from the introductory lecture that we start the course by just really focusing on the science of the hydrologic cycle, and then we can get more into water resources issues in the second half of the course with the science background. And at least that's my vision for the class. And we started with a basic introduction to the process of precipitation, and we covered what a watershed is and the area of a watershed and how that watershed captures water. And then we got into more detail last time about a concept of a water budget, that some of the precipitation that falls runs off into rivers and gets captured in dams or goes out natural flows. Some of the water infiltrates, and that infiltrated water may re-emerge in a spring or a creek. It may get taken up by plants and evapotranspire. Today we're really going to focus on groundwater itself, and I love this image given for groundwater by the USGS because it shows that groundwater is part of the hydrologic cycle. And that's something I want to emphasize during this talk and throughout the class. We think of groundwater as sort of mysterious. You drill a well, you pull the water out, and there you have it. But you must recognize that groundwater is part of the hydrologic cycle. And just like pulling water out of a river, when you pull water out of the ground, that groundwater was going somewhere. Maybe it was feeding a wetland. Maybe it was feeding a stream. Maybe it was discharging to the ocean, which is fine. But even in that case, you got to watch it, because if you, where my red pointer is, this groundwater pushing out to the ocean, if you pump out of the groundwater here and stop that big blue arrow from pushing out into the ocean, then the ocean groundwater can come seeping in, and that's a major problem in California. So this is just to say groundwater is important, and I hope that during this talk you learn more about it. The water budget unit, and you're going to keep seeing this because it's so important, focused on the amount of water lost through transpiration from plants. That is what determines the irrigation requirement for crops and lawns and all kinds of things. And it's a major part of the water budget. It's a very important part because the water that goes up to transpire gets lost in the atmosphere. The water that goes into a house and gets used and gets treated by a sewer plant ends up going back into the river. So more on that later. But and the next unit is urban hydrology. So we're going to talk a lot about this rain that falls on the ground and does not infiltrate and runs off into rivers and how land management affects that. Today we're talking about the water that infiltrates through across the soil layer there, percolates through the vadose zone, and makes it into groundwater. We'll start with, what is groundwater, and then why it's important. I hope this illustration is helpful for you. Groundwater is simply the water underneath the ground. I don't know if you've ever been at a beach and dug a hole deep enough, the water starts seeping in, like in this picture. That water is the ocean water. That is basically groundwater. So that's a photograph. The diagram on the right is a crude diagram that I made. It's a cross section. So following the red line, this is the beach, the layer, the sand, and the sand gets underneath the ocean layer at the shore where the waves crash in, and then there's the sea floor, and here's the sea level. But when the sea stops at the land surface, the water doesn't disappear. It goes underground. And so it forms what is called a water table. And that's the place where you first find water. So you can imagine if you dug a hole where my red dot is and dug down a few feet, pretty soon the water will start seeping in. And that's a very simple but very basic and true picture of what groundwater is. Here's a better, more detailed diagram that gets into more detail, obviously. First thing about this diagram to realize, soil consists of sediment, that is hard particles, and they're kind of stacked up in different configurations. If you really looked at a microscope, you could see it better. But in between the soil, they don't stack perfectly, so there's always a void space between these hard particles. And where there's no groundwater, that void space is full of air. And as you go down deeper into the soil profile, you see this place where there's water coating the soil more and more until finally you're where the soil is saturated with water. Groundwater is simply the water that occupies the space between the soil. Here's a better diagram getting into more detail. You see the land surface. You go down the ground through the unsaturated zone, you hit a water table. Below the water table, it's called a saturated zone. The only difference is that below the saturated zone, the space between the soil grains is full of water, and above the water table, the space between the soil grains is full of air. It works also for bedrock. If you're in the mountains, the granite there in the Sierra Nevada or the metamorphic rock or wherever you are does have void spaces. It's not a solid slab of rock there. Wherever there's a void space, if you're above the water table, there's air in the void space. If you're below, it's pretty much saturated full of water, and that is what groundwater is. This is a funky old diagram from a very old paper. It helps some people visualize, and other people it makes confusion. So if you don't like it, fast forward through this. But this white here represents the ground surface, and so you can see hills, the contours like our watershed, and you see these little blue creek here coming out, a nice flowing river here. That's what it looks like on the ground. If you peel back this soil, this dry soil layer, underneath, this is what's happening with the groundwater. And I don't know if you've wondered at times, maybe you're up in the mountains or somewhere and it's in the middle of August and it hasn't rained and the snow has melted months ago and the water's flowing like crazy in the river. It's wonderful. Where does that water come from? I don't know if you've ever wondered that. I have. And it turns out that for a lot of rivers like that, what's feeding the river is seepage of groundwater. That's the water table cruising along, expressing itself in a river and feeding that river. More on that later when we get into rivers. We'll talk about which ones are fed by groundwater and which rivers feed groundwater. Here's a very, very simple concept. The problems around groundwater that you'll get are, I think, the easiest of all because, and this is really how groundwater is managed. It's managed kind of like a big bathtub. So let's pretend the blue is water here. You have inputs to this bathtub of groundwater, and you have outputs. We're going to go into what the inputs are. Rainfall is one of them, obviously. But if you have more outputs than inputs, then you're going to have a change. Your groundwater table is going to drop. Your volume of available groundwater is going to decrease. Conversely, if your inputs are greater than your outputs, the groundwater will recharge and recover. And this is a huge concept, simple as it is, because we find out that for California and for actually most of the world, our biggest hope to store water is as groundwater. And there's going to be a couple of little article reading assignments around that. So here is a conceptual basin. I have this paper from the USGS tagged in the module introduction. You can feel free to download it and read it. There's great graphics and explanations. I hope to just hit the highlights here during this talk. And for groundwater, like I say, the recharge is the input. That's what's coming in. The discharge is what's leaving. And in between, you've got storage. So I would want you to be able to, without looking things up, be able to list out how groundwater is recharged. When rain falls on the ground and it infiltrates and percolates, that's a plus. More groundwater, yay. Surface water leakage. So some lakes, some rivers leak water out to the bottom and recharge groundwater. And then this is a giant one, especially into the future, artificial recharge, taking water and getting it to a place where it will recharge the groundwater. Then when it's living in the ground, the water is stored like a bank account. And then here's what people don't usually think about with groundwater, where it's discharged. So maybe it's discharging to a spring, a lake, or a wetland. If you see a nice wetland, it's very good chance it's fed by groundwater that's seeping into the wetland. It maybe is going into an ocean or a bay. Maybe some plants have tapped into that groundwater and are sucking it out and putting it in the air through evapotranspiration. It might just be groundwater leaving a basin through seepage. And here's where humans come in. We pump the heck out of it with our wells, and that's a discharge. The main thing here to realize is when you pump, you probably are decreasing discharge from somewhere else. You can't just pump out groundwater and irrigate a crop and have that water go into the air without somebody paying something. Because when you pump, you see, you don't add to storage and you don't add to recharge. So what's the story? It must take away from other discharge. Maybe that's not coming out too clearly, but it would be just like if you had a nice river going down through an ecosystem, and somebody says, hey, I want to take a bunch of the water out of the river and irrigate a crop with it. Your first instinct would be, well, wait a minute, that's going to have an impact because that water was doing something else. It was creating habitat, it was lowering temperature, it was creating habitat for salmon, or it was discharging to a wetland. You can't just pull water out of a river and not worry about it. Same thing for groundwater. You pull groundwater out of the ground, it's going to have an impact somewhere else in the hydrologic cycle. Here's another cartoon diagram that I think is helpful, and it gets right to the issue of what is sustainable groundwater use, believe it or not. So again, recharge. Here we have precipitation coming on the ground. It infiltrates, percolates through this dry soil here and hits the water table, and it will flow through this system. It could take days, maybe. Maybe there's a storm and it seeps in, and a few days later, the groundwater seeps out the river. It may take years. It could take centuries and even millennia to do its cycle. The point is here that if you are pumping out groundwater and you're pumping out what we call young water, that you can say groundwater age is it's born when the water hits the groundwater. It's your birthday for groundwater. So this is very young water in where my red pointer is now. Days or years you're pumping it out. So if you're using that water, you can be pretty happy that you're sustainable because your system is recharging within a period of years. But what we're doing in Texas and what we're doing in Arizona and the arid states, we're drilling deep into aquifers that haven't been recharged for thousands or hundreds of thousands of years. Basically, a lot of the groundwater we're using is left over from the last ice age. And there we have to worry about, is that really sustainable? Because you're pumping out water that isn't getting recharged. And so what's going to happen? It's going to drop. It's going to lose its storage. And so young water, if you're using young water, that may be sustainable. If you're using very, very old water, it very well may not be sustainable. And in effect, what you're doing is mining the water. It's just like digging out a finite amount of gold or something, because the gold ain't coming back, and this really, really, really old groundwater is not coming back in a hurry either. Real quick here, we have different relationships between groundwater and streams. Here is a typical case where the water table, the groundwater, these follow the arrows, is discharging into the river. And when we get into urban hydrology, and we look at a hydrograph of a river, which is how much water is flowing in it, you'll be able to see from the hydrograph where groundwater is coming in. Here's the opposite case where the river's flowing out and it's contributing to groundwater. You can get both ways. This is called a gaining stream because it's gaining water from the groundwater. This is a losing stream because it's losing water to groundwater. Here's another couple of cartoons that say the same thing. either these are both losing, where the water in the river is pushing into the groundwater, and here's where the water table has dropped way below the level of the river, and the river water percolates through an unsaturated zone before it hits the groundwater. Here is I'm hoping this is a clear diagram that illustrates what happens when you pump groundwater that you have to watch out for sometimes. Here's a case where you have the land kind of sloping down to a stream, rainfall. It's called a recharge area, where the rainfall comes in, infiltrates, percolates, and recharges groundwater. Now it's in groundwater. The groundwater is flowing along happily, recharging the stream. Somebody owns some property, and in California, if you own land, you can pump groundwater. And they drill a well into this water, and they say, this is great, there's plenty of groundwater here. And they start pumping. This is the diagram of a well, which is just a drilled hole in the ground, usually with a pipe in it with slots to let water in. And you start pumping the water out. Now this water was cruising along to the river, and it gets stopped by the well, and it comes out. And over time, if you pump hard enough, the stream goes from getting groundwater to losing water to the pumped well. And so this is a case where, it may seem like you're just harmlessly drilling a well and drilling and pulling out groundwater because it's there for the taking. But you have to realize, and we're realizing it more and more, that when you pump out groundwater, again, that water was doing something. It was going somewhere. And so when you pump it out and put it on a crop and have it evaporate away, there's other consequences to be aware of. Here's a couple of definitions. I'm not going to read them, but I want you to know what they are. And here's why, for California and for a lot of arid places, groundwater is such a big deal and for our future. The blurry chart here is a real important chart. So on the y-axis, we have capacity, and note the unit, million acre feet. So we're talking, all our problems are talking about hundreds of acre feet, 1,000 acre feet, or whatever, a couple of acre feet to irrigate the football field. In California, we talk about millions of acre feet. And this chart shows where we could be storing water, because we know into the future, now with climate change, it's not certain we may be getting more water, we may be getting less. What's more likely than not is that the water that we get will be less snowpack, more rainfall, and potentially more rainfall in short, intense events. So it would be always a good idea for us to be able to store water to use during periodic droughts. This is what's huge. The surface storage here that's dams. And you get up to here, dams can give us about 40 million acre feet of storage. And here's what so many people are excited about is future dams. Let's build some more dams. It's obvious. Look at the Sites Reservoir or other reservoirs. They can be huge. That will solve the problem. And what is proposed in all the new dam projects is this little bar here. We'll go from about 40 million acre feet of storage to 42 million acre feet of storage. Is that going to really solve our problems? That was a rhetorical question. Here's groundwater. So we have overpumped groundwater, and our groundwater table has dropped hundreds and hundreds of feet, which is basically kind of a disaster. And we've had to deepen wells, and we're digging deeper and deeper. And you probably maybe heard about, large corporate farms coming in that can afford to put in 1,000-foot deep wells, lowering the water table. Other folks, family farms that can't deepen their wells, or their wells are drying up. We'll get into the Sustainable Groundwater Management Act that's designed to address that. But the good news about us lowering the water table like this is that now we have vadozone, we have unsaturated earth that we could refill up with groundwater. And this is literally the estimated capacity of the ground to store water. Right now, we have 150 million acre feet of storage underground sitting there, not water, storage. So this is a big concept. I just covered it briefly right now. These two websites have really nice, like 3 or 4 page articles on just that concept of how to use groundwater to store our future rainfall excesses in a way that's much cheaper than dams and much more powerful. So that's one of the reasons why groundwater is such an important thing to understand for a water resources class. And here's what this is going on now. This isn't a future concept. Kern County in the Fresno area has been doing this for decades. Called the Kern Water Bank. And the concept is, so naturally, the Kern River comes out of the Sierra Nevada and it leaks water to groundwater. That's natural. Actually, before we invented the turbine pump in the 20s, the groundwater table was high enough that the groundwater contributed to the Kern River. But with our pumping of groundwater, we've lowered the water table hundreds and hundreds of feet. So that's the way we are now. And again, that's bad. But the good news is that vadose zone, that unsaturated zone, the soil with air in it, is now available to store water. And the way it's done is really pretty simple. You take water out of the river that you don't want to flow down the river and put it in a basin, put it in a puddle, and that puddle will then recharge the groundwater. Then the groundwater rises up, and then during, let's say, dry years, go ahead and turn on the wells. And so it acts just like a dam or a bank account, a savings account, any kind of reservoir. It's the same thing. Put it in when you have excess, take it out when you need it. So this is a little bit more detail, but I think you can get the concept of how as they call it, groundwater banking, literally. And this is the last slide for this lecture, which is going to be one of the longer ones, I guess. It shows sort of the image for what's going on with the irrigated agriculture in California. Here's the irrigated crop, the root zone, and the unsaturated zone. It kind of gives you the idea that, yeah, there's a lot of unsaturated zone there. And again, when we first started here, when we settled this area and developed it for agriculture, the water table literally in Bakersfield was at the ground surface. And we've pumped and pumped and pumped. We have taken out more than has come in for decades and decades. And as a result, the water table has dropped hundreds of feet. And so what's happened is these shallower wells needed to be deepened to get deeper groundwater. Here's also a concept: younger water on the top, older on the bottom. And so it's just to give you hopefully another image or picture of what's happening with groundwater. So that was a whirlwind tour. Do look up those articles. And there'll be some concept questions to answer for homework. What I want to do is just tie groundwater into the rest of the water budget more. So I might, instead of saying an area pumps out this much groundwater and it's recharged at this rate and pumped out at this rate, I might ask a little more convoluted, saying a farmer is irrigating 1,000 acres of tomatoes in Bakersfield, and they use 100% groundwater, and the groundwater is recharged at this certain rate. Is that farmer depleting the water resource or not? So that's the level of detail I want to get into. So you would look at what's the rate that the groundwater is being recharged, how many acre feet per year is going into the groundwater, and then how much is the farmer pumping out to satisfy the demand from the crop, which is basically the evapotranspiration rate. So more later.